So let's say we have a linear discrete dynamical system. X sub k plus 1 equals a square matrix A times X sub k. Let's let A be m by m. So our vectors are m by 1. For the process we're going to now present to work, we need m linearly independent eigenvectors. So this is the same restriction we have if we want to diagonalize A, but we're not going to make a diagonalization argument. The argument we are going to make is around the fact that if we have m linearly independent vectors, they are a basis of Rm. And any set of m linearly independent vectors is a basis, but we need these to be eigenvectors for our method to pass through. And then, because this is a basis, the vector that starts all of this process, x sub 0, can be expressed in terms of these eigenvectors. To see what happens next, it's probably easier to look at a specific example than try to do this in generality. So let's let A be the following matrix. And let's let x sub 0 be 1, 2. We need eigenvalues and eigenvectors. I hope at this point finding the eigenvalues and eigenvectors of a 2 by 2 matrix is fairly routine. It would be difficult if A were bigger than this. Actually, we don't need to do any work finding the eigenvalues because this matrix is upper triangular. Our eigenvalues are simply the diagonal elements. And we find corresponding eigenvectors, say 2, 0, and negative 2/3, 1. And we need to express x sub 0 in terms of these eigenvectors. X sub 0 is C1 times the first eigenvector plus C2 times the second eigenvector And again, it's my hope that at this point in the class, expressing one vector in terms of another is pretty straightforward. You do it with the Gauss-Jordan elimination on an augmented matrix. And in this particular case, the vector 1, 2 is 7/6 times this first eigenvector typo there, 7/6 times this first eigenvector plus 2 times this second eigenvector. And remember that this vector 1, 2 is x sub 0. Now, we're going to compute x sub 1. And we're going to do this without multiplying a single matrix by a single vector. Because x sub 1 is a times x sub 0. But x sub 0 is this. So we're multiplying a by this sum. Distributing the multiplication and moving around our scalar multiplication, x sub 1 is this. Okay, but this 2 sub 0 is an eigenvector associated with the eigenvalue 2. And this negative 2/3 1 is an eigenvector associated with the eigenvalue 0.5. And a matrix times an eigenvector is the scalar, the eigenvalue times the eigenvector. So this is 7/6 times 2 times this vector. And again, that's just the definition of an eigenvector, that A times the eigenvector equals lambda times the eigenvector. And similarly over here, we've got our matrix times an eigenvector. That's the eigenvalue times the eigenvector. So just as I promised, here's x sub 1 without doing any matrix vector multiplication. Our matrix vector products are all scalar products. thanks to the properties of eigenvalues and eigenvectors. Let's proceed and find x sub 2. And I'm not going to simplify these terms specifically because of the pattern we want to see emerge. Sorry, a student just came in, so I am not sure exactly what I was saying when I paused that recording, but I know what I want to do. I want to find x sub 2, and x sub 2 is a times x sub 1, and x sub 1 is 7/6 times 2 times this eigenvector plus 2 times 1/2 times this eigenvector. So a times x sub 1. Again, matrix multiplication distributes over addition, and these constants can be moved around at will. So 7/6 times 2 times a times this eigenvector plus 2 times 1/2 times a times this eigenvector. And once again here, a matrix times an eigenvector, a matrix times an eigenvector. So the last time we did this, we got our eigenvalue. Now we are going to get our eigenvalue again. And likewise over here, this matrix times this eigenvector is going to give us that eigenvalue for a second time. And in general, every time we multiply by a, it gives us the eigenvalue again. So x to the n, written in a non-recursive form, that is, so that you can calculate it without calculating any other x's, is this. So if we want, say, x sub 20, we don't need to calculate x sub 1 up to x sub 19. We just take 20 and plug it in to those powers.